Hi, everyone. Thanks for connecting today. Last year, we had a very good season of the seminar series on applied physics with particle accelerators. And to initiate the second season, we happily received today Massimo Chiari. He's the director of the LABEC, Laboratory for Environment and Cultural Heritage Studies. I met Massimo during some of the IBA conferences. I've been in LABEC in 2016, where he took me to know the facility. It's quite impressive facility, I would say. I'm quite happy to have him here. Thanks, Chiaro, for accepting this invitation, especially because I know the time is not so convenient for you, but it's very good for us to have you here. So I ask the audience to close the microphones and cameras and start again during the questions. And Massimo, thank you for your time, and the stage is yours.
Thank you, Thiago. Thank you, everyone, for being here after your lunch to listen to my, let's say, it will be just a brief presentation of our activities, present and past, about the application of ion beam techniques for environmental and cultural heritage studies. So as I was saying before, do not hesitate to interrupt, to stop me for questions, because I mean, this is just a friendly chat. Okay, I presume that all of you are already familiar with ion beam analysis techniques, so I am not spending here more than a few seconds. But as you can see in this picture, with ion beam analysis actually is a suite of different techniques that allow to determine elemental composition of let's say surface layers of samples. In many cases, the surface can be up to several tens or a few hundreds of micrometers via the detection of the particles or electromagnetic radiation emitted by atoms and nuclei in the samples after being hit by energetic MV energy ion beam. In the example that I will show you, we will mostly deal with proton beams of a few MeV energies, typically 3 MeV. Okay, our laboratory, I will start with a few pictures, is in Florence, in Italy. As I said, as the name says, we are mostly using ion beam analysis for environmental. Then I will maybe later detail that environmental for us is mainly air pollution and cultural heritage. You will see here some pictures about examples of analysis have been done in our laboratory. Our laboratory is doing with this 3 MeV tandem accelerator from high voltage engineering. So it's actually called a Tandetron ion beam analysis for fundamental analysis of thick and thin samples, for the profiling imaging with microbeam, and a lot of our application, as you can see from all these picture, are done with external beam. So when the sample is kept at ambient pressure, not inside a vacuum chamber. But with our machine, it is indeed possible to do also accelerator mass spectrometry. And among all the rare isotopes that can be measured with our machine, we let's say specialize in carbon-14 dating for cultural heritage applications, and so for dating in the field of archaeology and archaeometry. This is a sketch of the laboratory. This is just a scale model that we have on display just for dissemination. It's a 3 megavolt tandem accelerator. So we have 3 independent ion sources. 2 are used for ion beam analysis. So it's a 1 gas, 1 solid source, duoplasmatron sputtering. Then we have also sputtering multi-cathode source for AMS measurements. And then we have the AMS beam line, and then several beam lines for ion beam techniques. And you can see in this picture those that are ready, let's say, operative. And so we have one external beamline for PXY analysis on aerosol samples, one total IBA external beamline for cultural heritage. We have a total IBA in vacuum scattering chamber. We have an external microbeam where PXY and RBS could be performed. Actually, this external microbeam line is under upgrade. So actually, at the moment is not working. Then we have a pulsed beam facility for irradiation and implantation of even single ions in materials. And then there is under construction a specific facility for irradiation with the low energy protons, especially designed to test electronics for space applications. Okay, as written in the title, I will deal with environmental and cultural heritage application. Let's start with the environmental application. I'm showing here a picture taken from what is assumed to be the first paper dealing with ion beam analysis, even though at the time they are not called ion beam analysis, but if I remember, it was called something like nuclear chemistry. It is a paper from Rubin from 1957, and among the application of using nuclear scattering and nuclear reaction, what now we call RBS and nuclear and NRA, to determine elemental composition of samples irradiated with energetics, so a few MeV energy protons and deuterons. One of the first example is the spectra, RBS spectra of artificial aerosol samples. And so one of the first application of INB analysis is indeed RBS analysis of aerosols. And we will come later with the, let's say, more modern application of this specific technique. But also in the first paper of Johansson explaining the PXY techniques, one of the first examples was the application to aerosols, because indeed in aerosols is can be considered a thin target with a lot of elements. So you can see nicely a spectrum, a PXY spectrum with a lot of well-separated peaks. Okay, our environment for us means application to study air pollution. So to study particulate matter suspended in air. So maybe you are familiar with this terminology because it's often discussed also in the news for what concern the effect on health and other things. And so we will deal when we talk about particulate matter is called a PM 2.5, for example, or PM 10. According to the let's say to the diameters of the particles making this fraction. And you see here the comparison of the sizes of this particulate matter compared, for example, to human hair or pieces of sand. Why it is important to study aerosols, and also later I will discuss why it's important to study with ion beam analysis, because aerosol has an impact on the environment, because it's affecting let's say it's contributing to the climate forcing with the role that is typical opposite to the one of greenhouse gases, but the effect of this forcing is not well yet understood, so there's large uncertainties. So it's important to study and to try to reduce the uncertainty about the climate forcing of aerosols, because the prediction of let's say the future climate scenarios are based on an effect of aerosols with large uncertainties. So trying to determine the more precise value of the climate force of aerosols will also improve the models for future climate scenarios. Of course, aerosols have an impact on human health. The finer the particles, the deeper they penetrate into our respiratory system, and they can produce adverse health effects. But also, we are trying to make a short circuit between the environmental and cultural heritage. It has also an impact on cultural heritage, especially on those that are exposed external, because they can provide the formation of black crust, other chemical or physical damages to an opera. For example, in marble stages, or in Italy and Florence, we are full of this. Okay. Why can we apply IBA techniques? Why typically this field ideally can be studied using just chemical technologies? Because an aerosol sampling campaign typically produces a large amount of samples characterized by a small amount of materials. So for let's say comprehensive characterization of these samples, there's the need of using a multi-elemental, because with the single measurements you can measure more variables. High sensitive, because the mass is low, is very reduced. Fast, because you have to analyze a lot of samples and the beam time is not infinite. And then you need obviously quantitative techniques, and the fact that it's non-destructive is a plus, because then the same samples can be analyzed with different techniques. Okay. This is just an example of different kind of instrumentation that can be used to collect aerosols and the kind of samples, so the target that we measure with Imb Analysis that are produced. So you have, for example, large homogeneous samples like the one on the left. You have, let's say, spot-sized samples like the one in the middle, and then you have extended samples like the one on the right, where I will discuss more in detail about the analysis of the samples shown in the right-hand side of the slide, where the samples actually is just a continuous sample stretched over many centimeters, like here on the diameter of these filters. Okay. Okay. Why it is important to study elemental composition of aerosol samples, not compounds or molecular information, because one nice properties of aerosol particles is that they keep the same elemental or chemical composition typical of the source that has originated them. So when you analyze the particulate matter collected in one site, what is called a sampling site or receptor sites. So when you analyze the content of aerosol in one of these filters, for example, one on the left, you have a combination of the composition of the aerosols emitted by the different sources. Okay, so if you look at this picture, there is just a sketch, a picture of different kind of the main sources of pollution, natural and anthropogenic. So, for example, sea spray, mineral dust, or biomass burning, meaning natural forest fire. And you see that many chemical elements are characteristic of those sources. For example, for mineral dust, you have aluminum, silicon, calcium, titanium, iron. These are components of the Earth crust. For sea spray, obviously, you have sodium and chloride, but you have also magnesium and sulfur. And if you look at the anthropogenic sources like traffic, industrial emissions, ship emissions, or construction works, or also biomass burning, so burning of biomasses for example, domestic heating, or just to burn the branches of trees cut or something during, let's say, vegetation cuts. You see, you have specific elements that are tracer. So with source apportionment, the goal is to determine the weight, the relative weight of the different sources affecting a sampling site by measuring the elemental concentration. Okay, this is just a lot of statistics and mathematics, but just to give you an idea why it is important to also to measure single elements that can be tracer of specific sources. So this is just, now we come to more in detail to LABEC. This is the external bin setup for PIXI-PIGI analysis on aerosol samples. You see here that, can you see the mouse or this pointer?
Yes.
Okay, here is a sample holder where many samples can be placed. The proton beam is extracted from the bin line in this direction. Then we have two X-ray detectors for let's say mid-high Z elements, one X-ray detector for low Z elements, so for low energy X-rays, with the helium flowing in front just to reduce the absorption of the low energy X-rays emitted from the samples before reaching the detector that is about 13 centimeters apart. Then we have a magnetic deflector to divert or deflect the backscattering protons. I will discuss briefly why we use it. And then we have also a gamma ray detector for PIGY, because even though with PIXI we can detect elements starting from sodium, so from 1 keV on, even though we are measuring external atmosphere, in some cases, for some samples, the low low Z elements like sodium or even aluminum can be better determined by PIGY or by complementary PIGY measurements. And then you have a Faraday cap for beam current measurements for quantitative analysis. This is just a picture of a 3 MeV proton extracted into atmosphere from our previous accelerator laboratory that was in Arcetri. Maybe some of you know that Arcetri is a hill just outside Florence, where Galileo Galilei spent his last years of life, assisted by his daughter that was a nun. And so the advantage of using external ion beam, I know that you also have it, is that it is you can analyze samples of any size and composition without the need of, say, preparing the samples before the measurement to avoid effect like heating, charging, that could affect the samples, especially, for example, insulators when you're doing measurements in vacuum. And obviously, it has the advantages that you have to take into account: the fact that the extracted beam is losing energy, the energy is not so well defined because you have energy straggling. Also, the lateral dimension of the beam is increasing, and then you also have the effect of attenuation of the lower energy X-rays in the path from the sample to the detector. That's why to detect low energy X-rays, and so to detect low Z elements in the sample, we saturate with helium the path that these X-rays have to travel from the sample to the detector itself. Our setup has undergone a continuous evolution. Let's say you start here from picture from 2003, where we first moved to the new accelerator site, up to, let's say, the last update was in, let's say, several years ago. And the update was actually driven by the availability on the market of a new kind of X-ray detector for X-ray spectrometry. So the silicon drift detectors, it was initially intended as a position-sensitive detector for high-energy physics. And the SD detectors has indeed advantages with respect to the silicon lithium drifters, so the SILI detector that first were making our setup. So you see, in 2003 we were just using two SILI detector because you have indeed the better high energy resolution. There's no need to cool the detector at liquid nitrogen temperatures, and also the signal can be shaped at very, let's say, relatively short shaping times, like 1 microsecond or lower, and this allows you to withstand the higher count rates up to 10 of kilohertz. So starting with the first SDD coming in the market, so with the small area and small thickness, we started replacing the detector for low energy X-rays, and then we started replacing the detector also for the higher energy X-rays when the larger area and thicker detectors appear on the market. And nowadays we are using these two twin large area SDD array and let's say a small area 30 millimeters square SDD for low energy, for low Z element detection. Okay, you will see in this picture that in all this continuous evolution, we are using a different, but say always present, magnetic deflector in front of the detector that was looking at the low energy X-ray. So with no absorbers. The other detectors have some several hundreds of micrometers of Mylar as absorbers. The problem is that if you allow backscatter protons to reach the active volume of the silicon drift detector, you can reach unrecoverable damages, because these charged particles will damage the semiconductor. You see here, for example, the effect the noise as a function of the shaping time of a signal after radiation with such high fluence of 2 MeV protons. You see, this is just only reverse current, so it's not the semiconductor was damaged. And also you have short-term effects because you are facing a worsening of the energy resolution of the detector under beam irradiation. The worse, the highest the flux of backscattered protons. So how can we deal with this problem? So how we can solve this problem? So remove backscattered protons without using an absorbers, because in this way you will absorb also the low energy X-rays. So this is just solved by using permanent magnet to use it as proton deflectors or diverters. They can be shaped different sizes according to the maximum energies of the protons that they have to deflect and the size of the active area of the detector. So we have used it in the past different magnetic deflectors according to the different sizes of the SDD. So 7 millimeter square, 30 millimeter square, or I don't remember the one, 10 millimeter square. And you see that placing the deflector, even increasing the X-rays count rate, and so the backscatter protons count rate from the same samples, because obviously when you're doing PIXI, you are also at the same time producing the emission of all other kind of radiation, in particular also backscatter protons. Without the proton deflector, you see that the energy resolution was worsening as a function of the count rate of the backscatter protons, and with the deflector, this was constant and as good as it was before. Okay, the aerosols typically are studied by sampling for 24 hours. This is what typically requested by the laws. But there are some sources of aerosol that are changing with a shorter time scale. For example, because they're driven by meteorological patterns that can change on a few hours basis. So it would be important to be able to trace with high time resolution these pollution sources. That's why instead of integrating the aerosols, the sampling for 24 hours on one filters, we can collect the aerosols using this sampler. It's called a streaker. So it's a sampler where you have two filters that collect the two fraction of aerosols, the fine and the coarse, so PM2.5 and say PM10. While this collecting, this filter is slowly rotating and is moving by 1 centimeter per hour. So at the end of 1 week of sampling, you have a streak where every millimeter corresponds to 1 hour of sampling. So by shaping the beam, by focusing the beam just to analyze 1 millimeter spot, and by moving the sample under the beam, you can collect a series of spectra, and for example, 168 spectra for 1 week, and each spectra has can be used to analyze the composition of the aerosols on 1 hour time scale. Obviously, you can change the time of the sampling, so you can collect for 2 hours, and so increase the length of the sampling, so 2 weeks instead of 1. But the advantages of ion beam analysis is that these are the only one that can be used to analyze such kind of samples, because it is impossible to analyze this with chemical techniques like ion chromatography or ICP, because then you will need to cut these filters in pieces of 1 millimeter and analyze one at a time. So it will be also time consuming. Where with ion beam analysis, you can conform and focus the beam to such beams, to the beam size, for example, 1 millimeter, and then with high speed measurements, so for example, measurements lasting just a few tenths of seconds, you can analyze such a large number of samples characterized by very small mass of material in just a few working days. The sample that I've shown here is no longer produced, so that's why we designed our own INFN sampler that is called the size and time resolved aerosol samplers. They are now let's say, starting to produce several units in agreement with the private company that is actually designing the control and the pumping system, while the design of this streaker, of this new time resolving aerosol sample, is done by us. Okay, that's why now our application is called high-speed PIXI, because with a very efficient detection system for PIXI, and with the capability of extracting very high beam currents up to hundreds of nanoamps, it is possible to analyze the aerosol samples, so taking into account that they are characterized by a very small amount of materials, in just a few minutes or a few tenths of seconds. So we can analyze, for example, hundreds of samples in just a working day. I'm showing here some let's say applications of ion beam analysis applied to elemental to aerosol samples. For example, the importance of detecting and quantifying some elements that are tracer of mineral dust, for example, silicon, aluminum, calcium, iron, because let's say the ratio between these this element is a mineralogical fingerprint of the provenance of the dust. So, for example, it is possible to distinguish aerosols, mineral dust aerosols coming from local sources, like the background. These are sampled in Tuscany, or coming from long-range transported dust, like, for example, in Sahara, because you can see here, for example, the silicon to aluminum ratio is different for the mineral dust from Sahara with respect to the local dust in Tuscany. And also other elemental ratio can be used as variables to distinguish the provenance of elemental and dust. For example, Sahara dust can be long-range transported and reach even the coast of Brazil. And the measurements of aerosols, of the elemental composition of aerosol with high time resolution can allow also to trace specific sources, like, for example, traffic. And after the lead gasoline phase out, so where lead was a perfect marker for vehicular traffic. Now there are other elements, like, for example, iron or copper, that come from the wearing of the tires or from the catalytic exhaust. And so you can have this, you can see the nice peaks during the rush hours, and can also use other elements, like, for example, potassium, as a tracer of biomass burning. And you see, for example, in an example here in the countryside of Florence, and you see that, well, the peaks in the evening or in the night, suggesting the use of biomass burning for domestic heating, so pieces of wood in the fireplaces. Okay, most of the example I've given to you are for PIXI. But if you look at the composition of the average and ideal composition of the aerosols, most of the mass is made by carbon, nitrogen, and oxygen. If you look at the fraction of the mass that can be probed by PIXI, so, for example, element from sodium on, they're just less than 20%. So a very small amount. With ion beam analysis, it is indeed possible to determine also carbon, nitrogen, and oxygen using RBS, or actually EBS, elastic backscattering spectrometry, with proton beams. And here just an example. Using here in a very simple way RBS, because from the energy of the backscattered protons, you can determine the mass of the elements. So we are interested just in oxygen, nitrogen, and carbon. The area under the peaks is proportional to the concentration, because it is thin samples. Actually, as you will see, this is just a sketch. The shape of these peaks is is not symmetric, because we have to take into account that the fact that the aerosols have different sizes. So you have, let's say, large and small spheres, and they are distributed on the filter surface, and maybe it is not a full coverage. This has the effect of having a rough samples. A rough samples means peaks with pronounced left hand tails. The measurements in this case are performed in vacuum. This is just an example of the use of our in vacuum total IBA scattering chamber. So we are using EBS with the detector at backscattering angles to determine carbon, nitrogen, and oxygen. And we are using the detector at forward angle, so using what is called a particle elastic scattering analysis, or just ERD, to determine the hydrogen, because here we are dealing with the identical particle scattering. So no matters if you detect the forward scattered protons of the recoiling hydrogen, the double counting is not is prohibited. So you can determine hydrogen in a very simple way. But I'm interested in carbon, nitrogen, and oxygen. Here's just an example of a spectrum of EBS spectra of particulate matter PM10 collected on Teflon. We are using Teflon because it's made just by fluorine and carbon, while most of the other substrates have a lot of oxygen and carbon. So the contribution from the aerosols will be lost in the background. So the spectra is not, it seems not to be very complicated, but it's a very nice, a lot of features that can be simulated just using the later version of simulation codes like SimArray, implementing, let's say, cross-section that have been theoretically evaluated or experimentally measured, and using advanced physical models as the effects, like, for example, roughness. You see here, this is the fit of the spectrum, and if you look also at the different let's say, the contribution of the different elements, you see indeed that it is possible to distinguish the contribution of carbon coming from the aerosol to carbon coming from the filter, because Teflon is CF2, and then the contribution of nitrogen and oxygen on this in this spectrum. Okay, so just showing a simulation of blank spectra, simulation of loaded spectra. So it is indeed possible. The problem is that such simulations are time consuming. They're not trivial. So one idea that we had, so I'm just making a detail on this because I know that in your group, Thiago is also working on the use of machine learning or artificial neural network to analyze IBA data. So the idea was to, if you look at these spectra, they look the same, but there's not very strong changes of features, to use artificial neural network to analyze the spectra. It was just this is just a say boundary condition for the training set. And this is the comparison of the simulation of Teflon filters using NDF and SimArray. I prefer SimArray because it's more user-friendly. But at the time, the colleague that helped me in doing this, let's say, this first test was using NDF. So we tested both codes. Indeed, NDF has some problems because it's not treating properly the roughness, that is a crucial parameter to perfectly fit the left-hand tail of these spectra that are due to the roughness of both the Teflon filters and also of the aerosols that is deposited over it. And nevertheless, we were able to do some first training of the set, and then there is the results of the analysis, collaboration with this colleague from the Catholic University in Leuven in Belgium, Jelle de Mulmeister, that now is not working anymore in Imb Analysis. And you see that is not so bad, okay. And this is the output on to show the performance of these, let's say, very, very brutal artificial neural networks that almost 10 years ago, estimating the thickness and the roughness of the layer in the Teflon filters and the concentration of elements, let's say let's say training set, and what the network gives as a result. So this is a field that is not closed. There is still to work to be done, and I think that with SimArray, with respect to using NDF, better results could be obtained. So our experience is now leading in a further upgrade of the setup by increasing the number of SDD. So we are doubling the number of detectors in order to have a more efficient SDD array. And this array is modular in such a way that it is possible to remove one of two detectors and place a high-resolution pixie spectrometer based on a transition head sensor to do also high-resolution pixie measurements, to have also some information about, for example, chemical states that could be important as an additional tracer for the sources of the aerosols. Now, coming to the application of cultural heritage, you know that nuclear physics and cultural heritage, nuclear physics has helped cultural heritage since many times. For example, for accelerator mass spectrometry can be used for dating an object. Ion beam analysis can be used, for example, for compositional studies. And for example, for cultural heritage, IBA can be of help because the analysis of major elements, for example, by Pixie and Piggy, can help in materials identification. The provenance of the material can be obtained by analysis of trace elements, by doing measurements with high spatial resolution, like, for example, by micropixie, or even RBS for studying the depth distribution of elements. One can study the manufactured technologies. But indeed, the most of the, as shown also for the application to environmental samples, PIXIS is indeed a killer application in this field, because the fact that it can be performed with external beam is perfect for analyzing samples that are precious or have very strange and large shapes, and they cannot fit in a vacuum chamber. And so why? Also because indeed the ion beam analysis are non-destructive. I'm putting here a lot of pictures from the past and present application of external beam analysis in cultural heritage, different kind of materials, just to let you show that you can see here that can be analyzed large objects, small objects, paper, ceramics, metallic objects, paintings, oil on canvas or on wood, drawings on paper, semi-precious stones like lapis lazuli, and a wide selection of gold or gilded manufacts, from large one to the small ones. Most of the application are done just with milli beam, and some of these also for mid microbeam. This is just a picture of our dedicated external beam setup for total IBA of cultural heritage. We have one SDD, large area SDD detector for mid-high Z elements, detecting mid-high Z high energy X-rays, a small area SDD to detect low Z X-rays and thus elements, again with the helium flow in front of it. We have Piggy detectors. We have also an external RBS system. And then we have, of course, the extraction window. In all our external beam setups, the extraction window is a thin silicon nitride window, and a different way of normalizing the beam charge, because in this case we cannot use a Faraday cap, because the beam is not passing through the samples, because it's not as thin as aerosol deposit on a collecting filter. But in most of the cases, the sample is stopping the beam, so we are just relying currently on a beam chopper that samples the beam intensity before it will eat the sample. Here we have replaced the traditional typical 80 millimeter square CL detector with a large area 150 millimeter square SDD. This is the largest monolithic SDD available on the market nowadays. And you see here, for example, a comparison of the spectra of glass reference samples with these two detectors, and you see indeed the better energy resolution of the SDD allows you to better separate all the lines, especially when you have a cluster of lines, like, for example, L lines of high Z elements. And even though the count rate was such that you have some pile-up effects, it will not, let's say, destroy the readability of this spectrum. the application of external microbeam with the possibility of collecting elemental maps is indeed important, especially in this case more than in the application of on aerosol samples where they say the single particle analysis is not so important, because, for example, as you can see in these examples on the analysis of a painting from Andrea Mantegna, if you look at elemental maps around the eye of the Virgin or around the veil in front of the Virgin, you see that what appears to be yellow is indeed obtained by using by depositing small foils of gold. Okay, you see here gold, this part, and also gold in the veil. So to see that, I mean, there was also a technological effort in producing and in making this painting. Okay, even if the particular detail was very minimal. Okay. Our setup is a total IBA setup, so I will just provide you a few hints on, obvious hints on the importance of the synergy between PIXE and other IBA techniques like RBS, EBS, and PIGI. For example, PIXE and EBS are perfect companions. You see, for example, here from Star Wars, the astromechanical droids is complementing the protocolar droids, as you can see from the first opening scene of the A New Hope. And indeed, as written here, the strengths of the PIXE can be compensated by the strengths of RBS. For example, the fact that you have with RBS a depth resolution that is missing in typically PIXE measurements. On the contrary, PIXE is a high sensitivity and is very specificity. So, for example, it is possible to determine also high Z elements, while in RBS they will just not be separated due to kinematical effects. This is just an example of the analysis of a gilded sample. This is just a test sample, so it was prepared on purpose. So it has brass and with apparent gold layer on top of it, applied by using a glue, a mordant. Actually, it was not gold, but it was a copper foil. And by combining PIXE and RBS, it was indeed possible to determine the composition of the different layers and to distinguish copper and zinc coming from the top foil, the gilding foil, and from the bulk. If you have done just a PIXE, you could not distinguish the two, and you were not able. You could also say that there was not gold, but not distinguish and determine how the sample was manufactured. As regards to PIXE and PIGI synergy, here just PIGI is used as a sidekick of PIXE to determine just a small bunch of low Z elements, like, for example, lithium, boron, fluorine, and also sodium, for example, that cannot be detected by PIXE or whose detection can be hindered in some application. Okay, you see here some examples from the literature of, let's say, a sidekick of other heroes that are not so let's say minor, okay, with respect to the major hero. Just an example, the identification of lapislazuli pigment in paint layers. So lapislazuli is a blue pigment made by lazurite, and is a very precious, is a semi-precious stone. So the presence of this pigment in a painting means that there was also an effort in using this. So it was also the investment of money. Okay, the possibility of identifying lapislazuli by PIXE in canvas wood painted is hindered by the fact that most of the paintings have a varnish layer to protect it, and this varnish layer is thick enough to absorb low energy X-rays coming, for example, for sodium. That is a typical tracer of lazurite. You could identify lazurite mainly, for example, for sulfur, but the problem is that the sulfur X-rays often are let's say undistinguishable from the X-rays from M lines of lead. That was lead white was used everywhere, also as a primer in paintings. So it's indeed impossible to distinguish this by PIXE. It's just an example. In this painting from Leonardo da Vinci, blue was done by the lapislazuli. So if you use instead PIGI to determine sodium by using the 441 keV gamma radiation from this reaction, Since the energy of the gamma rays is 440 times the energy of the X-rays from sodium, it is indeed possible to determine the presence of sodium even if there is a varnish layer. So you see here an example of a blue pigment, and the blue light being lapis lazuli is identified by the presence of sodium with respect to another blue point where sodium was not present, and you see also X-rays from cobalt and zinc, meaning that this was a restored point, not an original one. And to produce the same shade of azure, it was used cobalt blue and zinc white mixed together. And we know that it's a restoration because these pigments were started to be used also from 19th century. So even at the qualitative level, it is indeed possible to distinguish original or restored or fake pigments. Indeed, it is not true that PIXI cannot give you information about the depth layers of on the samples that only EBS can give it. It is possible to retrieve the information about the layering in samples, for example, paint layers, by performing what is called differential PIXI, so different repeating measurements on the same spot by changing some parameters of the PIXI measurement, for instance, by changing the proton beam energy. So if you analyze the same point at different proton beam energies, for example, you can, for example, the range of the low energy protons can let's say, stop in the first layer. So you in the PIXI spectra, you will have the elements already on the first layer. You increase it, you punch through the first layer, and you will stop in the second layer, and then it appears also elements from the second. And if you increase, you punch through the different layers, and you will see so different X-rays appearing, for example, when you increase or reduce the energy, meaning that they are in a deeper or in a shallower layer. It is most semi-quantitative, but you can also do some, let's say, some trick to try to have it quantitative information, at least to say which layer is in front of the other one. This is just an example, semi-quantitative, of the identification of paint layers. Again, Madonna de Fusi, Leonardo da Vinci, where the study was the pink of the flesh of the hand of the Virgin, and by doing measurements at 4 different proton beam energies, it was indeed possible to reconstruct the layering. So the fact that there was indeed, say, a varnish layer, then there was a paint layer made by cinnabar, so mercury sulfide mixed with lead white to have the pink shade, and then there was a primer, a preparation made by lead white. It was indeed possible to distinguish this, let's say, sequence. But more, let's say, another more complicated example is here. This is a tin plate, so it's just a photograph on a metallic plate, and this is the PIXI spectrum at the 3 different proton beam energies. From the PIXI, from the differential PIXI, it was possible to give an idea about the ordering of the layer and which elements were in different layers. So you have an iron layer at the bottom, then a zinc one, another middle layer made by tin, chromium, manganese, and copper, and then a top of silver layer. And then using this structure and putting this structure in EBS, it was indeed possible to simulate a quite complicated elastic spectrum collected with external beam, so not benefiting of the high depth resolution and mass resolution can be achievable, for example, in vacuum with 2 MV alpha particles. And by using this structure as an input, a gas, it was indeed possible to provide the different concentration of the element and thickness of the layers, and have a very nice fit with a very low chi-square at the end. So where might where will we go with this? Let's say with the background of expertise that we have on LABEC. Obviously, when we are dealing with the application of accelerator for cultural heritage application, the main obstacle is the fact that most of the work of art are unmovable. If you look, for example, at frescoes, or they will not be moved because, for example, the insurance will be too high. So it will be impossible to have, let's say, Gioconda in Florence, or even at the accelerator on the Louvre, that is just in the basement. They will not have it for the measurements. So we have to change the paradigm, so the Muhammad and the mountain. So the idea is that to try to bring the accelerator where the work of art is normally is exposed or is resting, for example, in a restoration workshop. So that's the idea that we had. Try to build, to invent some kind of proton backpack to have an extracted proton beam like the one that we use in the Ghostbusters in the Ivan Reitman movie in the 80s, but it's not indeed possible. What is indeed possible is to have to use a high frequency RFQ accelerator from CERN, like they have been recently developed. Increasing the frequency of the RFQ means shrinking the size. So, for example, a 2 MeV proton accelerator is just 1 meter long. And so using compact, let's say, devices like compact ion source, compact diagnostic systems, compact detection systems, so on and so forth, is indeed, we have been able to build a compact accelerator that is just 2 meters and something more long and half a meter in width, weighing just only the accelerator a few hundreds of kilograms. Indeed, then there will be also a not negligible weight of the ancillary equipment, like, for example, the cooling system, the system to produce the high frequency, and so on and so forth. But it is indeed transportable. Low power consumption, meaning that it can be plugged into a main, also in a museum. And using just 2 MeV protons, you are just below the threshold of producing neutrons by irradiating elements like copper and iron. So it means that it's appealing for radio safety because it can be, let's say, switched on even in places that are not covered by radio safety rules. Okay, so that's my conclusion. My conclusion is that indeed you can still use the use of ion beam techniques in the field of cultural heritage and environmental application is not fading. It is indeed vamping or revamping, obviously using the proper equipment. So, for example, designing let's say a very efficient setup for application on aerosol filters, because you have to analyze a lot of samples, and you have to make the measurements quantitative, reliable, traceable, but lasting just a few tenths of seconds. And also in cultural heritage by the design of portable instrumentation. Okay, and I would like to thank you for my attention. Maybe I talked a little too much. I'm just showing here the logos of 2 projects that are supporting our activity. One is Radiate, that is a EU project as an infrastructure project of making network of ion beam laboratories in Europe. And the other one is Actris, is a research infrastructure for aerosol clouds and trace gas. So also for climate, where most of the people working there are not nuclear physicists, where nuclear physics is just a minor actor, but our laboratory is a European reference laboratory for elemental mass determination in aerosol samples. So we are just making like a calibration center for this kind of analysis by other European partners. And I would like to finish by giving this advertisement that the Radiate project is also offering transnational access to our facility, the one that I've shown in this presentation. And we have still a few hundreds of hours of beam time to be offered. The main target is obviously European user and associated countries, but there is also a quota, about 20%, for non-EU users, so people from, let's say, from Africa, from South America, so from Brazil, for example. And there is not really user-friendly submission system, but if some of you is interested in doing measurements, I can help you. Okay. Indeed, there is also a fee to pay the travel of the applicant, but it's limited to 300 euros. So I don't think that the travel from Brazil to Italy will cost will be not so cheap. But I mean, this is, if you're interested, you can send samples, we can analyze, and we can share the results. That's all. Thank you for your attention.
Thank you, Massimo. Fantastic presentation. I'd like to start the discussion session. Does anybody have questions to Massimo? I have a couple of them.
Okay.
I will start making some just to break the ice. Yes, exactly. I like it, the many points of your presentation, but I will start with questions about the schematic of your accelerator, because I got curious about two things. One is the irradiation chamber that is under construction that you mentioned. Can you say a little better what is planned to be done there?
Yeah, I have no better let's say drawing, but the idea is there is an agreement between the Italian Space Agency and different research agency in Italy. One is indeed INFN, to provide the facilities for irradiation of, for example, of electronic components. So there are other laboratories in Italy, INFN. Paola knows National Laboratory of Legnaro. They have the facility working since many years in irradiation with high energy ions, and also not only protons, but also different other kind of ions. But there was a gap, still a gap, for a low energy protons irradiation. Low means to MeV. Okay. So the idea is to have a facility where we have, let's say, a stable beam, okay, a fixed beam, and we have a stage where we can mount for example, the electronic board to be irradiated and to be moved, so it can also make some, let's say, not only scan, but you can irradiate in different positions, and with the possibility of course, of recording the dose. And this beam line is also equipped with a chopper, with an electrostatic chopper, like we have in the other beam line with the pulsed beam. So it is indeed possible to have also, let's say, bunches of protons hitting the samples. The same, let's say, the same technology or configuration is used in the other beam line, where you have the pulsed beam, where it is used to deliver from single ions to hundreds of ions in a single bunch, to study, for example, the linearity of electronic system coupled to a detector for nuclear physics or high energy physics, or to implant, for example, our colleagues are implanting low energy silicon to produce, let's say, single emitting centers for quantum application.
I see. That was my next question. I mean, the pulsed beam. If you guys are intending to go into the direction of diamond vacancy color centers, right?
Yes.
For emitting single photons and so on.
Yeah.
This apparently is a trend. Either the test of electronic devices for space applications and quantum materials seems to be a trend for a laboratory like ours, right?
Our, let's say, the negative side of this is most of the people doing this at a very high level, or with the strong connection to the funding agency or funding institution, are from solid state physics, or and they prefer to use different technologies than, let's say, accelerator, for example, to implant ions or to produce the devices. So we are, let's say, we are striving a little bit to enter this community.
Yeah,
While in other let's say research areas, the accelerator are just let's say we say in Italy brought on a plate. I mean, they are shown you as a main tool, like for example in Australia or in New Zealand. In Italy, this is not the case, because I mean, this activity was not stemming from an idea of people working with accelerators, but people working without accelerators. So
yeah, I participated in a training in the IEA on quantum applications of accelerators.
I remember the ideas. Yes.
And I feel it out of the place over there, because it's more dedicated to low energy single ion applications.
Yes. Now you have also you can buy system for low energy single ion implantation. There are the companies in the UK and are dedicated. True. For example, the problem of our accelerator is to reach low energies. So the energy needed to implant, for example, silicon has to be reached by, for example, by let's say slowing down using the foils. I mean, some tricks that can then.
Yeah, that's true. That's why I asked about the diamond vacancy color centers, because this apparently is more suited for the high energy accelerators like the one in LABEC and at Banfi. Does anyone have questions to Massimo, or can I keep making okay,
Manfredo.
Of course, I need to make questions. It's not possible to fight.
Thank you.
Excellent talk, Massimo.
Thank you, Manfredo.
Thank you very much. And an amazing laboratory. I didn't know it.
Thank you.
So it's really amazing what you do there. I have some very few questions, but I like, if you can, tell us a little bit more about your magnetic deflector on your low energy pixel detector.
Yeah, of course.
It's 8 centimeters long.
Yeah,
it is pretty long. So
I can.
And where are the poles? I didn't understand exactly from the drawing or from the picture. Where are your poles of your magnetic?
Manfredo, your sound is not quite
the
good.
sound is not, but I've understood. I mean, if I go to the, I will try to. Where is it? I don't know where is it. Maybe I'm losing it. Okay, I don't know where is it. Okay, maybe the. Can you see it? Okay.
Yes.
If it's not in presentation mode, I mean the field was 0.5 Tesla, more or less, because there was permanent magnets, 2 slabs, and according to the size of the active area, so the diameter of the detector, we have to divert more or less. So we have to apply the force for more time. So that's why we need to have the protons travel increased length in the magnet in the magnet. So the larger the surface of the SD detectors, the longer needs to be done the magnet. There is a very simple formula, let's say, basic physics to calculate, to shape the deflector.
Can you show more or less the magnetic field lines?
The field lines are in this direction. They're perpendicular to the path. So you have let's say a deflection. We are not taking into account the fact that the beam has a divergence. We are not taking into account the fact that here not in vacuum, is in air. So the beam is indeed slowing a little bit, even if it's not, maybe it's a second order effect while it is traveling. So it will be diverted more at the end of the deflector than respect to when it's entering. So there is a formula I've not shown you, but I have let's say I have a PDF with all the passages and also the mechanical drawings for making these in its own machine workshop. And okay, and that's all. Okay. Obviously, this means that the solid angle subtended is reducing accordingly. Okay, so
I'm asking Massimo because I tried to make
here.
such...
Sorry. Here in this solution, that is the one that we are currently using, and taking into account all the dead layers, the detector is about 30 centimeters away. We have a solid angle that is just a few milliradian. Okay, but it's more than enough for Pixie of low Z elements, because the cross section for low Z is increasing, so it can compensate.
Perfect, exactly.
Alfredo, apologize, but just in this matter, the solution should be put 2 magnets instead of only 1, and make a more homogeneous distribution of the magnetic field in your. You could put one each side instead of.
We have 2. We have 2 slabs. So we have 2 slabs.
Oh, I'm sorry. I thought. Just
No. We have 2 slabs. I don't know if you see my. So it's just a parallel plate magnet. So we have the field perpendicular. Then there is let's say soft iron to confine to avoid the stray fields, because you have the detector. Okay, and that's all.
I'm sorry, my friend.
Thank you. No problem, Nemi. And the second question, Massimo, is a little more, let me see, political probably.
Yeah, okay.
You said for cultural heritage applications, a small accelerator and all the ion beam analysis technology together would be a very nice solution.
Mm-hmm.
But I'm guessing that we also need to have a let me see, comprehensive data analytical system. Mm-hmm. Because of course the people that do cultural heritage, they don't want to analyze spectra, they don't want a report, and as simple as possible. It's more or less like the physicians that use nuclear resonance on your whatever leg, but they don't look at the spectra, they look on things similar to a X-ray radiography. Mm-hmm. And they don't want to know the details of the machine. And I think we need to improve a lot the data analysis to get results that are acceptable and quick. Is that more or less?
Of course, in most of the cases, like for example, when you're using, let's say, a strong competitor is XRF, because XRF is intrinsically simpler and thus more transportable. Exactly. You can. Our laboratory has, let's say, a fleet of transportable XRF scanner that can, let's say, produce what is called a macro area XRF. So large area scan with elemental maps with the very large, or even, let's say, 10 centimeters or even 1 meter by 1 meter. And of course, most of the information is qualitative, because in cultural heritage, for restoration, just the distribution of elements is more than enough, because then they can correlate with, for example, UVVs or infrared images, so on and so forth. So for most of the application, the qualitative information is more than enough. And this can be, except if you want to look at low Z elements like boron, lithium, where we have an application in our laboratory with people from the geology department, where they are studying ceramics from the 18th century on, and they have come to the conclusion that the presence of boron in the ceramic can be used to date, let's say, or to distinguish, let's say, a more modern or ancient ceramic. Ancient meaning also 19th century, and this can be done also by Piggy. So we are analyzing a lot of, let's say, collections to try to reinforce this idea. So this could be a very nice tracer to determine, even without a lot of, let's say, quantitative data analysis, just the presence of boron, yes or no, it could be made to distinguish. But nevertheless, in some cases, it is important to achieve also a quantitative analysis. And then can be done, for example, by IBA more than the XRF, because it's more complicated. And in some examples that I've shown to you, they are not the only one. There are also other. Well, for example, here in this example of the elemental mapping, this is just qualitative information. Where is gold? Is it associated with other elements? Okay, just enough. While in other situations, like for example, when you're using, when you are interested also in the manufacture, how is structured the samples, it is important to complement the X-ray spectrometry information with, for example, charged particles like RBS or also PIGE. But with RBS, it is indeed possible, as I've shown here, to obtain a quantitative study of the composition that could not be easily achieved just by PIXE, okay, because it's just, let's say, semi-quantitative information. That's why the system that we are designing will be based on PIXE and then also possibility to PIGE and eventually RBS, with the possibility to do quantitative analysis. So my effort is to try to apply as much as possible quantitative and traceable data analysis to the results, not just saying, okay, there is iron, there is copper, and that's all. How much, which uncertainty, okay, and so forth. And that's why we are now still playing, let's say, ping pong between, let's say, GUPXWIN and RBS, back and forth. Then there are also some, let's say, codes for standardless PIG analysis. There are Siemens array itself can do it. There is the PyGreco code from the friends from Democritus. There is the area code from your the other Portuguese-speaking colleagues from Lisbon, and also there is the huge effort will be to try to make NDF a working, the user-friendly program, because I mean it's indeed a mess to work with that program. I know if you are let's say familiarity with the NDF, but it's not such user-friendly.
Thank you, Massimo, very much.
You're welcome.
We are not so familiar with NDF. We prefer the multi-Siemens array.
Yeah, of course, of course. Yeah. That's why, for example, it will be, unfortunately, we're not able to listen to your talk at the last IBA conference because I was, at the same time, I had another meeting. The fact of, let's say, trying to add also, let's say, electromagnetic modules to Siemens array, like possibility of using PIXE. Because otherwise now you have the two families are, let's say, they're not so much connections, so GUPXWIN and Siemens array. So
that's true. Well, I have the record of the presentation if you want.
Yeah. If you can send it, okay.
Yes. So Ugo, do you have a question?
Yes, I do, Massimo. That was a very nice talk.
Thank you.
I am one of Thiago's students, so I'm about to begin my master's, so I'm gathering information, gathering references. And something that interests me is that the atmospheric physics group here at our institute, they also analyze filters, but they use a different technique. They use X-ray fluorescence. And I would like to know from you if you have any thoughts on that, on how we compare this technique with PIX and RBS. How can we separate them? Which one's better? If they have any major differences?
Okay. XRF spectrometers are widely used in laboratories for elemental for the analysis of aerosol filters. I mean, because they are, let's say, turnkey instrumentation. And we also have one in our laboratory, and we will also soon procure another one, because, as I've said before, as our role of calibration center for elemental analysis of aerosols with the techniques like XRF, PIXE, ion couple, ICP-MS, we need to have the possibility to test different instrumentation that can be used in the laboratories. XRF is a good tool to determine elemental composition in aerosols. That's not problem. What the problem is the throughput, because typically the measurements can last 1 hour, even more, less, with detection limits that are in some cases worse than what can be obtained by PIXI. Okay, our PIXI setup is especially designed to have, maybe it's okay, I'm not boasting, but is indeed the only one in the world that can reach such levels in terms of, let's say, detection limits and speed of the analysis for aerosols, okay? This is just a matter of how much samples do you have, okay? So, for example, if you want to analyze 20 samples per day by putting the samples in a carousel and doing the XRF analysis, that's okay. But if you want to analyze, for example, hundreds of samples in a few hours, you cannot do it with XRF. So it depends also but it is okay. Of course, there are some information that cannot be obtained by XRF, okay, or some samples that no. But typically, XRF is a we had also an XRF system that was used to determine, for example, the high Z elements in the samples, because it was more let's say sensitive than typical PIXI measurements with silly detectors. Then when we changed our array to SDD, we were able to reach detection limits that were better than the one obtained with the typical XRF spectrometers.
So it's basically because by what I understand is the equipment is also has lower dimensions. It's smaller.
Yes, of course. It's also a small scale equipment, so it can sit in a normal chemical laboratory. So, but I presume that if you're interested, there could be some, let's say, some connection, because, for example, with PIXI, since they have a high, let's say, increased cross section for low Z elements like sodium or silicon, I mean, earth crust elements, PIXI can be very important for mineral dust. You can have an information just for a mineral dust in just a few minutes with respect to the hours. So you can, we are doing the same. So we are just doing very, say, flash PIXI measurements for mineral dust, and then more long measurements of all the elemental composition with XRF systems.
Oh, wow, that's a nice answer. So thank you very much, Maximo.
You're welcome.
Definitely, that's a good point. There's also this thing that PIXI can be quantitative, right?
Yes.
XRF
XRF the same if you are dealing with the thin samples, because they are reference samples. Okay, so it's not a problem. You can do it.
So Nemitala, do you have a question?
I have a question about this RFQ you are showing in your slide. Why plan to go to 2 MeV protons instead of 3 MeV protons? I can't understand. Why do you guys choose that?
Okay, it's just
this would be a dangerous energy level, right? Because then it could replace.
No. I mean, I was. Let's see. Can you see it? Okay, can you see the presentation?
Yes.
Yeah. I mean, each of these module is half a meter, and it's 1 MeV energy. So one module is 1 MeV, 2 modules is 2 MeV, 3 modules is 3 MeV. So more modules, more length. So we had a goal to have 2. So 2 MeV, 2 meters, 200 kilograms. Obviously, more modules, more cumbersome and bulky, let's say, power system to have the RFQ. Okay,
can't you change your design to get a model of 1.5 MeV instead?
No. Yeah, they could have. Yes, if you change the energy, you have to reshape the structure inside. So and also the acceptance of the initial beam. So they have designed these modules because they were using as injector for a high energy proton beam for radiotherapeutic applications. And so we were using the design. Of course, if you want to have 3 MeV, you can redesign the quadrupole expansions to have in half a meter 1.5 MeV. But then it's a lot of work in let's say simulation and also in brazing in the mechanical work. And then we decided to stop at 2 MeV also for let's say for radio safety issues.
Sure.
Because in this way we could safely bring the instrumentation also in a restoration laboratory without any problems.
Okay. Thank you.
Okay, you're welcome.
I have a question about this machine as well.
Yeah.
I've seen in another slide that in your electrostatic accelerator you can do aerosol analysis with currents, beam currents from 10 nanoamperes
hundreds
to hundreds.
Yeah.
Do you believe you can achieve this level of currents with this RFQ machine?
Yeah, no, that's the problem. RFQ is a high intensity machine. So there the problem is to reduce the beam.
No, to
Because,
reduce.
I mean, we are not, let's say, diving into the dark because there is an RFQ with 3 MeV in a laboratory near Rome of another, let's say, research agency. It's called Enea, where I have done some tests of pixie measurements using pulsed proton beams to check that indeed pulsed beam with such let's say high average peak let's say current could be indeed feasible doing pixie measurements, and indeed is possible. But then the challenge is to reduce the intensity of the beam, and then can be done in different ways. For example, you can reduce the amount, the intensity of the beam from the source. You see here is not these two colors here are quadruples. You can play with these to defocus the beam after it's exiting the accelerators, or you can let's say collimate the beam in order to reduce. But then you have let's say average current around 1 nanoamps. So that's the problem. You try to reduce the current. RFQ is microampere, so it's not a problem. That's why it's used as injectors. Okay.
More questions?
Currently, the system is the source is working, the control system is working, the vacuum system. Now the system is in CERN to do the acceptance test of the coupling of the source with the accelerator, and after it will come back to do the final test with the detection system.
Great.
Sorry. Just a moment.
He has another meeting. Acho que ele marcou outro. Esqueceu de avisar.
Temos uma presença no Mikael.
No. Here I am. Sorry. It was just my son was asking something.
Okay.
No problem.
My son is also asking something here.
It's nearly dinner time, so it's just say.
Okay, just to finish all the questions, I have one concerning the future. I mean, I see that in your laboratory you are constructing a new setup for irradiation. You are working with pulsed beams for implantation. You have this idea of a portable accelerator, but in the sense of the whole field of IBA, do you see a future for this? I mean, what are the trends that you see? Because I see that you and your facility is highly connected with the future. That's my question. I see a lot of developments, but I just want a general picture of what's your opinion about the future of IBA?
Most of the, let's say, the more striking technological development will be for us, for my colleagues, in trying to design other portable accelerator. Let's say, because there is also already the idea to try to extract a microbeam to have also not only millibeam but microbeam with this system. The idea is, for example, to change the the radio frequency source from proton to helium to have, let's say, a compact helium RBS system with 2 MeV helium and a small scattering chamber. So to have, let's say, a dedicated small accelerator for material science with helium. That could be another possibility. Okay, large improvement will be, for example, trying to have, let's say, high resolution PIXI detectors. But then, okay, you can try to replace one detector with a more, let's say, innovative one. But currently, we are not thinking of large, let's say, technological improvement in IBA. We are looking at new field of applications. For example, one, let's say, trending application is forensic science. You have, for example, your colleague, Johnny Diaz, at the ion implantation laboratory. There's also a lot of application in forensics. Then you need, of course, a lot of connection with the people doing this kind of science. So I think that MV Analysis a lot of important role in multidisciplinary or interdisciplinary application. Okay, so for example, environment, climate, forensics, let's say food fraud, so on and so forth, and also cultural heritage. Of course, there are some applications like, say, quantum, the designing of quantum, let's say, devices. It's of course an important field. But as regards our laboratory, I think that most of the technological improvement will be in the direction of this small accelerator, different specialized small accelerator.
I see. Yeah, I agree with you. This is, I would say, finding new collaborations and designing compact systems seems to be definitely a road to go. Saying in the perspective of a third world country with not so much investments in science, where I could test the compact systems, I would say that for us, it's always a bottleneck, the data processing, right? That's why we are always investing in speeding up the data processing with artificial intelligence and so on. We always find in the place that we find the collaborators, we do the measurements, and then we spend a lot of time doing the data processing. It's always problematic.
Yeah, but for example, if you are doing, for example, for PIXI and in, let's say, the application of PIXI to environmental samples like aerosol filters is perfect, because thin samples, the analysis is very not trivial. I mean, is very straightforward. So you can indeed measure, and the day after have the quantitative analysis. You have not to spend 1 day for each RBS spectra that you have. So if you have hundreds, it means hundreds of days of analysis. Okay,
yeah,
or hundreds of students doing each one spectra per day. Okay,
yeah.
So that's.
So
yeah, most of our applications are PIXI based, and this helps a lot because the analysis is fast. Okay.
Most of our applications are on RBS.
RBS, so the RBS is more as a nuisance. Okay. Yeah.
Questions? So what I will do is stop recording.
Okay.